Good morning, students. Today we are going to look into lecture topic toxic release and dispersion models. This is the content of the lecture. So let's look into the introduction. So during an accident, process equipment can release toxic materials very quickly. So there can be explosion, ruptures of pipeline, tank or a truck, which can cause release of chemicals, which also causes vapor or gas release of the toxic materials. So incidents such as Bhopal actually gives us a lesson that we should have an emergency planning to minimize such occurrence and the consequence of a toxic release. So toxic release and dispersion model are used to estimate the effects of a release on the plants and community. So this toxic release and dispersion model takes into consideration the human working in the premise and also staying in the surrounding, as well as the environment, the flora and the fauna. Therefore, the stack emissions, so stack emission, this is chimney, stack is chimney, so the gases that is being emitted from industrial plants. So the emissions from industrial stacks are also regulated to protect the human and environmental health. So one is release, toxic release by accident, but we can also have pollution or toxic release through stack emissions. So that is also regulated. So industrial facilities are required to obtain permits to emit into atmosphere. So first of all, we need permits for stacks, which demonstrates compliance with the regulations. So when we want to apply for the permit, the dispersion models are used to assess the impact of the point source emission. So the stack emission is usually for gas, but if you see air pollution, they are both particulate matters, solids, as well as gas. So particles less than 20 micrometer behave same as gas and has low settling velocity. It will continue to be taken away by the air or gas from the sac as well as the air in the environment. Particles bigger than 20 micrometer have significant settling velocity. Therefore, only gases and particles lesser than 20 micrometer are treated in dispersion models. Others are treated as particulate matter. So we assume effluents leaving the stack with sufficient momentum and buoyancy. So the hot gases will continue to rise. So a dispersion model is essentially a computational procedure for predicting concentrations downwind of a pollutant or toxic source. So we have a toxic source at one point, then how far can the toxic material spread downwind, I mean toward along the wind direction to the surrounding. So that is dispersion models. You will want to know impact at the point as well as the surrounding. So the dispersion models are usually used in environmental impact assessment, risk analysis and emergency planning. Okay, next let's look into risk assessment and release mitigation. So risk assessment based on toxic release models. So first, for us to reach the dispersion model, we first have to identify the situation that can lead to a release and then we can evaluate it to a poor condition to the worst conditions, and then we develop a source model. So we looked into these two parts in the previous lectures. So once we have this information, then we do the dispersion modeling, because we want to know how far the material could spread, and from there what could be the consequence to the people and our surrounding environment. From the dispersion models, the outcome of the risk assessment is we are able to develop emergency response plan, engineering modification to eliminate sudden release, then enclose the potential releases by adding some vents or scrubbers. We can reduce inventories, that means the amount of chemicals that are being used, to ensure safety, to reduce the risk, and add area monitorings to detect leaks from the possible places like valves. And we can also introduce engineering controls to eliminate hazardous levels that can cause leaks. That means we control the hazardous level to avoid leaks. So in conclusion, so we need the basic information about chemical release, like the point of release, and then the relevant source model and the dispersion model. From there we can predict the release impact. So if the hazard is accessible, yes, we can operate the process, but if it is not, then we have to revise it. So these are some of the release mitigations that can be done to reduce toxic release hazards. Okay, these are more release mitigations, countermeasures, and emergency responses. Okay, dispersion model provides information on concentration versus distance. So it describes the airborne transport of toxic materials away from the accident sites. So we use source model output as the input for dispersion model. So this input of the source model gives us subsequent event model and vulnerability model. That means this gives us what happens when the material is out of the source. Okay, so it only applies to gases or vapor releases. There are two main types of dispersion models. Well, you would have seen it as well. So one is plume models, where you see there is a dispersion from a smokestack. So it is long and continuous. Then there's also puff models, where it releases in clouds. Okay, so because these models, this plume model and puff models, can be of any size, it can be of any shape, any length. So we have to define the dispersion. So for that we use Pasquill Gifford model. This is one of the models, and this is widely used for air pollution for dispersion models. Okay, so the solution of the Pasquill Gifford dispersion model is to assume that the materials spread out in a normal Gaussian type distribution. Gaussian comes with a double S, yeah. So these are the model basis of a Gaussian distribution model. So these are the informations that we require. So we want to know for a localized point source such as stacks, what is the general appearance? Is it plume, or is it like in clouds? And then the exit, at which height? Does it rise to an additional distance? So that will depend on the buoyancy of the hot gases, and it's also called plume rise. Reaches distance where buoyancy and upward momentum ceases. So that is the final distance when the momentum ceases. No, buoyancy will bring it up, go up to a point. Okay. Then what is the exit velocity from the stacks? Okay, so what is the emission rate, and if there's any wind blows in a direction. Okay, so these are the informations that we need for us to design a Gaussian model. So if you have a stack or a chimney, so usually this is the case. This is how the dispersion will happen. So this will travel to a short distance height, and then it will become consistent here, right? So in our model, we assume there's an additional height from this point to this point. Okay, so this is the middle point, and then it emits in, it spreads in a Gaussian model. Okay, so these are the planes that we will consider. So you have Z plane going upwards, then you have X plane. Okay, this is the basis of the Gaussian dispersion model. So the stacked gas is always transported downstream. The dispersion in vertical direction, okay, the vertical direction to above, is always governed by atmospheric stability. The dispersion of horizontal plane, okay, this direction, is governed by molecular and eddy diffusion. That means how the concentration of the material changes from the point source and then towards the downstream. So x-axis refers to wind direction, and then z-axis refers to vertically upwards direction. Y direction refers to transverse to the wind. That means that is the opposite of the wind direction. Okay, so this Gaussian dispersion model will always do a stacked gas where it's transported downstream. Okay, so towards it always uses the wind direction. Concentrations are symmetrical about y-axis and z-axis. Okay, so this is a graphical view of the axes and the systems or the basis of the Gaussian dispersion model. So if we have a stack, okay, and then there's an emission, okay, so we have, so it's going this direction. So that means the wind direction, which is the x-axis, is here. So this is the x plane. Okay, so it's going upwards. The vertical, direct vertical to this is the z plane, and the transverse to wind, okay, the transverse to the wind is y-axis. So this is the wind direction. Okay, x, y and z is equals to 0. That is at the base of the stack. So in Pasquill Gifford dispersion models, as the plume is swept downwind, so this is your z axis, this is your x, and this is your y. So the plume is moving in this direction. So as it is swept downwind, the concentration profile spreads out and decreases. So you see at the beginning the concentration is high, very high. It's not very spread. But as it travels downwind, the spread increases, the concentration decreases. So this is also another visual of the instantaneous value. That means immediately when the plume occurs, this will be the plume size, but after an hour there will be an average that covers a wider area. Sorry, so this is where it starts. Okay, this is your y, this is where it starts, is the wind direction. So it starts small, and then in the beginning it's not very, it's a smaller dispersion, but after an hour the dispersion gets bigger. So it's different. The average is always different than the instantaneous value. So this one is the plume shape, and this is the concentration profile. So as you notice, in the beginning the concentration was high, then as time passes, as it spreads, the concentration decreases. As it spreads, the concentration decreases. Okay. The Pasquill Gifford dispersion model has dispersion coefficients which are defined in the direction of wind, in a crosswind direction, and with the elevation. Okay, so this is elevation. So these coefficients are correlated for 6 different stability classes. Okay, this table here shows us the stability classifications. Okay, there are 6 stability classes. A is very unstable, B is moderately unstable, C is slightly unstable, D is neutral, E is slightly stable, and F is for stable. So regardless of wind speed, class D should be assumed for overcast condition, day or night. So because when it's neutral, so it should be assumed for overcast conditions. Okay, so and if you notice, these smaller letters of A, B, C, D and E has got its meaning as well. So A is surface wind speed, which is measured at 10 meters above ground. So these are the different ranges of the wind speed. Okay, so this is smaller than 2. Okay, 2 falls in this class, so anything smaller than 2 falls here, and this is bigger than 6, so 6 falls in this class, so this is above 6. Okay, and then B corresponds to clear summer day with sun higher than 60 degrees above the horizon. Okay, that is B, strong. So you have a day, then you have night, you can have solar isolation and cloudiness. So during the day, these are atmospheric stability classifications. Yeah, then you have C, which is a daytime with few broken clouds with sun 35 to 60 degree above horizon. And then finally we have D, fall afternoon, this one slight for a cloudy summer day. Then E refers to cloudiness, is defined as the fraction of sky covered by clouds. Okay, so if this is the coverage, this is cloudy, then less than 308, then it's clear, so it falls in the different atmospheric stability. Okay, so let's see what causes unstable daytime condition. So the unstable daytime condition is a time where the plume will actually behave in accordance to the environment. So it is like you can't accurately predict what will happen to the plume. It can grow in different direction with the changing environment. So what usually in the daytime we have a sunny clear sky, so you have sun light, so that gives us visible radiation to the ground. So there will be a lot of sunlight, so that causes the heating of the surface. The ground surface heats up. So when it gets warmer, the lighter air will go up. Okay, so there is a large scale of vertical motions during the daytime, and the cooler air from the top will actually travel down. So this is the process. So there will be more transport of lighter air, especially gases, vertically upwards. Okay, so that is the and then when it combined with wind, then it becomes unstable. Okay, then we can have a stable nighttime condition where the sky can still be clear, but there is no sunlight, so there's only infrared radiation to the space, so it's the other way around. So then the surface is going through cooling process, so the warmer air will stay at the top and the colder and denser air will stay at the bottom. So the vertical motion, that means going upwards, is suppressed by the density because it's heavier, so it will stay here. So that is the nighttime stable condition. Then we can also have neutral condition. Okay, so what happens in a neutral condition? You can have relatively high wind speed, but the motions are not affected by the buoyancy forces. They are not affected. The vertical air motion due to shear stress. There can be vertical motion, but because it wants to break free from other particles. But other than that, there is no big effect where it grows vertically. Okay, so the surface is also minimally heated or cooled, so there isn't much impact on the vertical motion. So that is a neutral condition which can happen at day or night. So these are some visuals of the conditions. So when it's strongly unstable, if you notice, you see it grows big and it goes downwards, and then suddenly it goes upwards, and then the plume also grows bigger. Okay, this is the unstable condition. This is a stable condition wherein the plume size is about, it grows but not drastically. Okay, so there is no up and down motion here in the stable condition. So there are few tables and figures which are important in the Pasquill Gifford dispersion model. Okay, so this table 5 actually is table 5.3, gives the stability classes to be used in the Pasquill Gifford models. For a given set of conditions, we can actually determine the stability class to use. For example, if we are given daytime and then a certain temperature, then we can actually choose whether it's A, B or C. Okay, and then we have figure 5.1 and 5.11, which is actually a function of the downward release, which is a graphical information from the table. Okay, so this is the table. So for different stability classes, see, we have different equations. So this is y direction, and this is for x, and this is for z, and these figures are the representative of the y and the z axis. X axis has got a range. So from these conditions, we can identify the stability classes. Also from the environment condition, we can identify the stability classes, and then we can find out the y axis impact and the z axis impact. So this one was for Plume dispersion model coefficient. So we also have for puff model dispersion. So in path model, the x and the y axis is equals. Okay, so that means the effect for the transverse of the wind condition is equal. That's the assumption. Okay, so there are three conditions as well for unstable, neutral and stable conditions. Then this is for y direction and this is for z direction, and this is the representative figure for these equations. Okay, let's do a quick example here. For a stability class A, what are the values of sigma y and sigma z at 1 kilometer downstream? Okay, this is sigma, yeah, this symbol is sigma. Okay, it also means standard deviation. So let's first use the graph and then we try doing using the equation. Using the sigma y graph, okay, so these are the different stability classes, the graphs for it, and this is the x value. So the question says 1 kilometer, so that is 1000 meter. So if I match it straight to stability class A, so in this case A and B is the same line, so I get the sigma y as 220 meter. Then for stability for sigma z, again I look for 1000 meter and I match it to stability class A. Okay, so if you notice it's matched to the linear models. Okay, then I get the value of sigma z, that's about 310 meter. So in this slide I've not shown the calculation method, but what you can do is you can look for stability class A, then this is the equation. You can substitute the x into meter, 1000 meter, so you will get about the same value as you got in the graph, and same go to sigma z. So you look for stability class A, the range 1 kilometer falls here, so you use this equation, substitute x, and you get about the same value. Okay, let's look a little bit into Plume model. In previous slides, we knew that there can be two types of dispersions. One can be plume and the other can be puff. Okay, so we saw the dispersion model in the previous slides, and then let's see how we model the plumes itself. So assume the plume has developed, hence it is continuous. So when there's a plume, it's continuous, therefore there is no dispersion coefficient in the direction of flow. Okay, so it's assumed there is no dispersion of the plume. Okay, so there is no dispersion coefficient. So this is the equation for Plume model in the x, y and z direction. Okay, so this is for y and z direction, and then we have an additional term. So it's the same equation, but it's the positive here and negative here. So why is that so? Because in the Plume model we also assume when it hits the ground there will be a reflection. Okay, so that's why it's a plus and a minus reflection. Okay, that is this plus and minus. So if let's say it's a particulate, if we do not have a particulate, that means we do not have something heavy that could probably hit the ground and reflect, or if we have a particles that will react with the ground, either reacts and then it doesn't reflect, or there is no particles that will reflect, that means it's all light gases, then we can actually remove the reflection part. Okay, so we can reduce this equation. So we can also further reduce the Plume model if the source is at the ground level. Okay. So let's look into the puff model. Often in accidents, the releases are instantaneous, and therefore there is no plume developing in accidents mostly. Yeah, so there is a need to use a different dispersion model, and that is based on a puff. So in puff models, we need a dispersion coefficient in the wind direction. It assumes that it is in the same as in the crosswind direction as well. So the dispersion coefficient is only defined in three stability classes, which are unstable, neutral, and stable for puff models. Okay, so this is the extended model for puff at height r, hr. Okay, so we have all three y, z, and x taken into consideration. However, we can also, since we assume that this y and x has is equals, okay, so we can actually reduce this equation to this, where it specifically uses y and the z condition. So it assumes there is no interference or limitation to dispersion in any direction. So x naught and z naught are location of center line of the plume. Okay, so where it starts, so the x-axis also becomes the center line. So y is taken as base of the stack, the y naught. Z naught is h. So q is the emission, and then you have average wind speed, you have concentration, which is in gram per meter cube, then you have a horizontal and vertical standard deviations in meters. So this is what it means. So it says when the plume starts, so the x-axis becomes 0, 0, and then the direction of plume is so at 0 it's 0, and then this is the y direction. Okay, this is the x-axis, and then you have a y direction this side. So as you see, it grows in a y direction, and then it also grows above. Okay, so that's why we use y directions, and then so it's, and also the z, because it grows up. Okay, so this explains the terms that are used in the simplified point source at elevation h without reflection for puff model. So this part gives the concentration at the center line of the puff. Okay, this one is the concentration as you move in the sideways direction of the plus minus of y direction, and then this one is the vertical direction as it goes up. It moves in the sideways and it also goes up. Okay, so if we use a ground source level, then we do have the x value. Okay, so if it is a ground source, so this is the equation we use, and then from that ground source, the coordinate system moves along with the puff. So the ground source, when it moves along the puff, then it becomes the y and the z. equation. Next, let's look into integrated dose. So when a person is standing in a fixed location and suddenly a puff passes over, so that person will receive a dose that is the time integral of the concentration, because a puff will be highly concentrated, because it comes suddenly in a high concentration and then it disperses out, then it dilutes out. So if you're standing in a certain distance and you have a puff passing through, then you're affected by the concentration, your coordinates of x, y, and z, and the time of exposure. So for a person on ground at distance y cross v, so we use this equation. And for a person on ground at center line of the flow, so you are at the center line, so that means only the first equation, only the first parameter, only the first equation matters. Okay, this one has a distance, this one you are in the center line of the flow, this one has a y direction, that means it goes sideways. Okay, so you have a different impact. So puff model can be used for continuous calculations by representing a plume as a succession of puffs. So that means this puff model can also be representing a plume. Okay. So when do we assume it as a plume? Is when there is a succession of puffs. There are few puffs. Okay, then we can also represent it as a plume. But so we can calculate the number of different puffs, the time to form puffs, effective height, continuous leak, and instantaneous leak into smaller puffs. Okay, so these are some of the informations that we can extract from the puff models. And then both the plume and puff model utilizes an effective release height, so it has a height that it initially releases. So this is caused by the momentum and buoyancy effect. So for a stack release, we have an equation that can give us the additional effective height. So if something is being released from the stack, it can actually be calculated. Okay, this is for HR. Okay, so that's all for toxic release and dispersion models. So let's look into the examples of how we use the equations and models that we have just learned in this lecture. Right, let's look into our first problem. A burning dump emits an estimated 3 grams per second of oxides of nitrogen. So what is the average concentration of oxides from this source directly downwind at a distance of 3 km on an overcast night with a wind speed of 7 meters per second? Assume the dump to be a point ground level source. Okay. Firstly, when it's a burning dump and it's emitting, so usually it is a plume. Okay, you see a continuous flow of emission. And then the other important information is overcast night. So this is the information we're going to use to find the stability class. If you remember this table in our lecture, okay, it says if regardless of wind speed, class D should be assumed for overcast conditions, be it day or night. So our stability class here is going to be D. So for a Plume model dispersion. So we can use this table to find sigma y for class D and sigma z for class D. Okay, so our x here is 3 kilometers, so it's here. So you use the second equation to identify the sigma z. Next, the question also states that it is a plume model. It is at ground source. The source is at the ground level. So we are going to use this equation. And because we assume it to be a plume model, so that's why we'll be using this equation for ground level. Yes. So these are the informations that we've already gathered. So it's a plume, and then it's 3 kilometer distance, the x. Then you have a velocity, and then it's an overcast night, so it's stability class D, and we've decided which equation to use at ground source. So first thing first, at ground level, the concentration, the Z is 0. Then we assume center line where y is equals to 0. So first we can find our sigma y and sigma z from the table, and substituting the 3,000 into the x value. So we get the sigma y and sigma z. So because these two terms are 0, so this equation becomes 0. This part of the equation becomes 0. So we are left only with the first part of the equation to solve. Okay, so now we have all the informations, so we just substitute to the equation and we get the results. Okay, this 3 gram per second is the flow rate, the Q. This is the U, and the sigmas. So it gives you a concentration of the emitted gas at 3 kilometers. Okay, so let's look into the second example. A factory emits 20 gram per second of SO2 at a height. So there is a plume rise, and then it gives you a wind speed. So at a distance of 1 kilometer downstream, so sigma y and sigma z are given. So if it is given, you use the given value. It can be different from what you find from the graph. So if it is not given, then we would have to look up from either we calculate from the equation, or we look up in the graph. So what are the SO2 concentrations at the center line of the plume? That's the first question. So we're looking at center line. So when it's center line, the x, y, and z is 0. And at points 60 meters to the side and 20 meters below the center line. So if below, you're talking about vertical movement, that's for z. Side lines, we're talking about y movement. Okay, so let's just solve the first question first. So this is the Q, U, sigma y and sigma z is given. So for a center line, y is 0, z is equals to h, it's also 0. So which means the h is equals to 0. At center line, z is equals to 0. So that gives us a 0. So that reduces the equation to only 1/2. Then when we solve this, we get the concentration at the center line. Okay. Then the second question is at 20 and 60 meters. So this equation will not be 0. So the y is sideways 60 meter, and then the z is given sideways, which is the z is below. So then below means negative. So you get negative 20. So it can be negative, positive, because you're going to square it, so you're going to get the positive value. So substitute it. We already know this value of this term, we calculated previously. So we just have to calculate this part, and you get the emission at this coordinate. Okay, so this is another plume example. Okay, this is the third example. So it's given is stability class C. You have a height, we have a flow rate, wind speed. So what is the ground level concentration at 0.5 kilometer, that means it's 500 meters downwind along the center line? And they have also given the sigma y and sigma z for us. So how do we calculate? Again, so it's along the center line, but we have a h. Okay, we have a height. So because it's along the center line, so the y becomes 0. So which is why the y part becomes 0. We still calculate the h, and you calculate the front part of the equation, and we get the concentration at 500 meters downwind. Okay, then I gave you an in-class an exercise, a take-home exercise. Please give it a try. So that's all for this part of the lecture. See you for the next class.